So you hop on an airplane. Thousands of feet in the air, you're headed home, and you look out the window to see that one of the engines suddenly fails. Amidst the panic, the pilot chimes over the intercom to calmly remind everyone that the aircraft is designed to fly safely, even on one engine. That level of reliability isn't an accident, and this mechanical beast is going to carry you and a 100-ton commercial airliner safely home. Hey class, I'm Sam Anderson, mechanical engineering intern, and today we're diving into what may be the most overdesigned engine in all of human engineering, the gas turbine engine, also known as the jet engine or turbofan. Just one of these core units can produce up to 110,000 pounds of thrust and will cost anywhere between $20 to $45 million. Now, how does a gas turbine engine work? So overall, it's a pretty complicated process, but the turbine engine is a four-step process that utilizes a thermodynamic cycle paired with mechanical systems to generate thrust. Let's break into it. So first we have the intake stage. The engine drives a row of inlet fan rings to suck in a large volume of air. Once the aircraft is up to speed, the surrounding air can be somewhere between 500 to 650 miles per hour. For commercial planes, it's ideal to get an extensive intake without breaking the sound barrier, so airspeed in the inlet greatly exceeds the surrounding air due to suction. To do so, the inlet fan blades can spin 10 to 25,000 times a minute, inhaling up to 3,000 pounds of air per second. Next, the air is squeezed through the compressor. Here, the fast-moving air has to climb through layers of rotors and stators, which are curved metal rings meant to break the airflow, slowing down air and increasing pressure. After the air is extremely compact, it's funneled into the combustion chamber for the next step. All the friction and pressure from rubbing against the stators makes the air very hot and very dense. By the time it gets to the combustion chamber, the air pressure can be anywhere between 30 to 50 times the pressure of the surrounding air, making it ideal for efficient heat transfer. On to combustion, this is where the magic happens. The jet fuel is ejected and ignited into the compressed air to produce a high-energy gas stream. These gases can exceed 2,000 degrees Celsius, twice as hot as molten lava. To avoid melting, engines need to be manufactured with cobalt-based superalloys that resist both intense temperatures and internal pressure. Combustion is able to produce a ton of energy through the combination of chemical fuel combustion and a thermodynamics process known as the Brayton cycle, which is a process similar to diesel that allows continuous flow. Finally, the high gas energy stream is blasted out the engine as the excited gas rapidly expands. There's two important components of the exhaust that allow the plane to move forwards, the turbine and the exhaust thrust. Before exiting the engine, the high pressure gas spins the turbine, which drives the compressor and inlet fan so that the engine can keep sucking in air. The remaining energy is converted into velocity as the gas accelerates through the nozzle, propelling the engine forward. The nozzle is aerodynamically shaped to direct the exhausted air into a high-velocity jet stream, which is also why we sometimes call it a jet engine. This rapidly expanding jet stream produces thrust as mass is accelerated rearward, providing over 100,000 pounds of forward thrust, keeping planes in the air. So the next time you're on a plane, remember there's one of the most advanced machines ever built working non-stop to get you home safely.